Welcome to this video about Earth observation. Before we dive in, let me outline the topics. We will have a look at meteorological endeavors, specifically the European missions. Then we will talk about geophysics and how Earth observation excelled the research in this field. And as a last subcategory, we will discuss environmental monitoring and one of its most important missions. Finally, we will have a glimpse at the potential of small satellites and constellations in the future of Earth observation. Since the very beginning of space travel, Earth observation has been a main interest and driving factor for the development of space-borne sensors, since they offer a very unique perspective. The most frequent application of Earth observation in our daily lives is probably the observation of weather and atmosphere. Every major space-traveling nation has a meteorological mission in operation. The European Union has its own operation named EUMETSAT. This program has two kinds of satellites, Meteosat and METOP. Both of them provide data for weather forecasting. The third generation Meteosat constellation consists of 3 individual satellites. 2 of these satellites are imagers and the third is a sounder. One of the imager satellites was already launched in December 2022 from Kourou Space Center. In 2024 and 2026, the other 2 satellites will follow. The first of the 2 imagers provide a full image of Europe and Africa every 10 minutes with a spatial resolution of 500 meters. The second imager will provide a more rapid scanning every 2.5 minutes with a spatial resolution of 2 kilometers. Additionally, the lightning imagers acquires real-time data of intensity and location of lightning flashes. Meteosat orbits Earth at an altitude of 36,000 kilometers in a geostationary orbit. That means the field of view is constantly pointing at the area of interest in Europe and Africa. Therefore, Meteosat is a continuous source of data. This data provides information about fast developing severe weather conditions, standard weather forecasting and climate monitoring. METOP satellites have much lower orbits. At an altitude of only 871 kilometers above the Earth's surface, the 2 satellites can record data at a much higher spatial resolution than Meteosat. The polar orbits, however, do not allow continuous observation of the same field of view. Each satellite orbits Earth approximately 14 times a day. Therefore, the Earth spins underneath the satellites so that the observed area changes while the sunlight conditions stay the same. Together with NOAA satellites, METOP ensures that the area of interest is monitored at sufficient intervals for making precise weather forecasts and issue warnings. For instance, storm warnings at marine areas. A more subtle but not less significant use of spaceborne sensors is the measurement of geophysical parameters. These parameters include the Earth's magnetic field intensity and radiation intensity. A good example is the first US-American satellite Explorer 1, which was launched in 1958. It carried sensors to measure the cosmic ray count. These instruments recorded data that allowed the formation of a theory about a radiation belt by Dr. Van Allen. This theory was then proven by further investigations during the mission of Explorer 3. Another very impactful mission, which was dedicated to research the magnetic field of our planet, was ESA's SWARM. SWARM is made up of 3 identical satellites and it was launched in 2013 from the Cosmodrome in Russia. The satellites have a very unique shape with a deployable boom of 4 meters length,
which makes a total length of 9.1 meters. The boom carries highly sensitive instruments, mounting the sensors on the boom, reducing the magnetic noise in the readings originating from the electric systems within the satellite bus itself. Apart from attitude sensors, there's a magnetic field vector sensor, an absolute scalar magnetometer, and an electric field instrument. The targeted orbit of two of these satellites were at an altitude of 460 kilometers, and the third satellite was launched into an orbit with 530 kilometers altitude. Besides radiation and magnetic field, gravitation is also a determining parameter. The Earth is not a perfectly homogeneous sphere, therefore minimal changes in the geoid shape of our planet have an impact on local gravitation. A way to determine the deviation of gravity from a perfect sphere is to measure orbit distortions of satellites. Gravitation directly affects the orbit, therefore tracking a spacecraft with lasers and measuring the orbit deviation provides information about the gravitation of the geoid. Another important field of Earth observation is environmental monitoring. This subcategory deals with recording changes of the land surface. The focus lies on vegetation and resources. This field of research started with the launch of NASA's Landsat missions in 1972. The program is still in operation. That makes it the longest continuous Earth imaging mission. In September 2021, the 9th generation of Landsat satellites was launched. Landsat 9 is operating in a sun-synchronous orbit at an altitude of 705 kilometers. Every 99 minutes, the satellite circles Earth, and after 16 days, the satellite reaches the same field of view, meaning that two images of the same area can be compared at least 16 days apart. Landsat's instrumentation consists mainly of two components: one multispectral imager and a thermal infrared imager. They are both improved versions of the predecessor. The multispectral imager has 9 bands, of which each has a ground sampling distance of 30 meters. The thermal infrared imager has 2 spectral bands with a ground sampling distance of 100 meters. A practical example of using data collected by missions like Landsat is, for instance, vegetation monitoring. I had the privilege to get technical insight into environmental monitoring during my master thesis. The project aimed at building a simple convolutional neural network to access potential of AI in satellite image analysis. Overall, the task the AI was trained for is to find tree canopies in a RGB imagery without additional spectral information. This approach, combined with a large availability and high frequency of satellite images these days, can provide a deep insight into the global dynamics of vegetation. In 2008, the Landsat archive was released to the public free of charge, which has caused a huge increase in availability of imagery. A lot of images were retained in the global network of receiving stations outside the actual archive. Therefore, the public availability of these images has doubled the number of images available. Since ESA's Sentinel-2 satellites entered operation, Landsat and Sentinel together are imaging the entire land surface twice a week. If you want to access the public available data of Landsat, you can find the links down in the description. With the current developments in technology, small satellites have become more and more important. Especially in Earth observation missions, small satellites hold an enormous potential. Due to cost effectiveness, large constellations can be realized. Constellations can increase the time, resolution, and ground coverage massively. To avoid any misunderstandings here, I will refer to the ESA's definition of satellite categories, which are small 350
to 700 kg, mini 80 to 350, and micro 50 to 80. Small satellites can be designed with two different approaches. One approach is to use commercial off-the-shelf technology, and the second approach is to utilize miniaturization of sensors and instruments to design a high-performance Earth observation mission. The advantages of small satellite missions compared to bigger satellite missions are that more frequent missions allow for faster iteration cycles, which makes those missions also highly suitable for research and development. Furthermore, it leads to a larger variety of missions and may serve many more different use cases. And lastly, it involves local and small industries much more than conventional missions do. However, it is worth noting that small satellite missions are more complementary than they are competitive to large satellite missions. One particular use case of Earth observation instruments is the imaging spectrometer. The Landsat missions, for instance, rely heavily on multispectral sensors. Hyperspectral data can increase the precision when spatial resolution meets its limitations. Therefore, it is useful for mineral exploration, environmental monitoring, or forestry on a global scale. With state-of-the-art technology, it is possible to realize hyperspectral missions with mini satellites as light as 100 kg. Combined with formations to make use of distributed aperture systems, this approach has a huge potential for future research. To sum it all up, we have discussed that since the beginning of space exploration, Earth observation has been a major topic in research. Be it for weather forecast, understanding of geophysics, or environmental monitoring, till today satellite missions observing our planet are still of significant interest. And with the ongoing technological developments, it's most likely that this will not change in the future. If you want to dig deeper into the topic, follow the sources I've linked in the description. Thank you for watching.